All right, this is section 13.4. This is on the chain rule. So this is related to the chain rule that you know from Calc 1 for taking derivatives. It's actually a more general version of that, but it'll feel very different than that. So think of it as an independent thing. And so let me begin by giving an example. And then we'll talk about this example, and then we'll talk about the chain rule. So let's say this. Suppose we know the following. Suppose you know that z is a function of x and y. So z is something like x squared y plus y cubed. But then you suppose you also know that x is a function of s and t, like maybe this, and y is a function of s and t, like maybe s squared t. Right? So really what this says is that y is a function of s and t, because think of the phrase is a function of as depends upon. So this is saying z depends upon x and y, but they themselves depend upon s and t. So really, at the end of the situation, z is a function of, in this case, s and t, in this particular example. So it should make sense to write, for example, partial z, partial s, and partial z, partial t. These two make sense. They should make sense. How can we find them? So one way, which is not the way we want to do it because it sort of avoids learning something new, which will be useful, but it's not wrong in this case, but I just want to illustrate it in case it crops up, is suppose you wanted to find, say, partial z, partial s. Right, what you could do is you could take your z and you could literally just fill in x and y. So x is s cubed plus st, y is s squared t, and you could just then do partial z, partial s. Right? There's nothing mathematically wrong with this. Right? However, there's another way. That other way is the chain rule. The chain rule is sort of a very different way, which turns out to be useful not just here, but in other situations. So the chain rule is another way. So the chain rule says the following. So I'm going to give this in sort of a, I'm going to give it for this particular example, and then we'll do a few more examples where you'll see how it applies to different types of problems, but it's helpful to step through this with a particular example in mind. So, step 1. Let's say first, draw a tree representing the function dependencies. Now, if you wonder what the heck I mean by this, that's okay. We'll step through it. So in this case, z is a function of x and y. So we'll branch z to x and y. X is a function of s and t. So is y. That's the first thing done. So this is what I mean by tree representing the function dependencies. Right? So then what we do is, along each branch, put a partial if it's more than one variable, and a d if just one. This sounds far more confusing than it is. In our case, what we do is, I'll go back up to this picture, z is a function of both x and y, so those will be partials. X is a function of both x and of both s and t, so those will be partials. Same for y. So in this case, everything's a partial. Next example, we will have a d in it. Then what we do, so we bullet this so we see. Then what we do is find all paths from z to s. In this case, it's z to s because we're looking for, in this problem, we're looking for partial z, partial s. So there's a z on top and there's an s below. So in our particular case, we can go from z to x, let's see that, and then from x to s, that is one path from z to s. Or we can go from z to y, and then from y to s. So that's the second path, two different paths. So what we do is find and multiply the derivatives along each path, and add paths. So what that tells us here is the thing we're looking for, partial z, partial s. So the top path goes from z to x, and then from x to s. So take a second to digest that. I'm multiplying those. That's from z to x, from x to s. I take those derivatives, I multiply them. But I could also go from z to y, and then from y to s. That's the second path, the lower path. So this is the chain rule. The chain rule says this step right here is really, the picture is just helping us write down the chain rule for this problem. Then what we do is find those derivatives. So what we do is we go back to the beginning, to where our functions were given, back here, and we actually just find those derivatives. So partial z, partial x is 2xy. Partial x, partial s is 3s squared plus t. Partial z, partial y is x squared plus 3y squared. And partial y, partial s is 2st. And then last thing is we do is we, let's say, substitute to the final variables. So in other words, what that means is, let me give it some space here so we're sure we do, is everything in our tree ends with s and t. So everything should be an s and t at the end. So I have a 2xy, x is s cubed plus st. That's x, y is s squared t. Then we have 3s squared plus t. We have x squared, which is s cubed plus st squared plus 3y squared, s squared t squared times 2st. So all we did is we substituted for x and y what we knew for x and y. And this is the final result, right? This is the same thing that you would get if you did, let me label it this way, right? Like this step back up here. If you did that, which would be really messy because this is a messy calculation, you would get the same result that we did here. This chain rule result is like a little bit tidier. It's a little bit easy to keep track of things. There's a little substitution to do at the end, but it's certainly less messy. So what I want to do is a few more examples of this to show you some of the different things that could come up when we do these. So take a second, make sure this makes sense. I'll clear the screen off, do a couple more, and then we'll do an application. So the next one looks a little more complicated, but it's not hard. I just want to do it to make a specific point. So I'm going to say find, say, dz ds. And the conditions are as follows. Notice it's a regular derivative I'm looking for. That's okay. So z will be x squared plus, say, square root of y. We'll say x is e to the 2s. We'll say y is s squared t. And we'll say that t is s cubed. So there's a lot going on here. Let's take a look. All right. First thing I'll do is draw the tree diagram. So just to make sure things make sense. So z depends upon x and y. X depends upon only s. y depends upon s and t depends upon s. So notice that the branches of this tree are different lengths. No big deal, no problem. What we're looking for, well, let's fill in all the partials and d's. So z is a function of x and y, so those get partials. X is a function of only s, that gets a d. Y is a function of s and t, those get partials. T is a function of s, that gets a d. Now, notice at the end of the day that z is a function of s and only s. So, dz, ds makes sense. Because at the end of the day, z is a function of s and only s. Right? So the chain rule says, all right, there are three different paths from z to s. So, dz, ds. This is next. dz, ds. I could go from z to x, and then from x to s. Notice I have a partial z, partial x, and then a dx, ds. That one corresponds, just so we're clear, to this path up at the top. That's that one. Then next one we do is the second path, which we could go from z to y, and then from y to s. Let me put some multiplications in there. That one corresponds to here and then here. Or last but certainly not least, we could go again from z to y, and then from y to t, and then dt, ds. That corresponds to going down here as well, and then here, and then here. Oops, that's purple. Let me label that. That's this guy right here. Then what we do is we calculate all those using the information at the beginning. This could be messy. Let me back this up. I have no idea how awful this is going to be off the top of my head. So partial z, partial x is 2x. dx, ds is 2e to the 2s. Partial z, partial y is 1/2 y to the minus 1/2. Partial y, partial s is 2st. Partial z, partial y is again 1/2 y to the minus 1/2. Partial y, partial t is s squared. dt, ds is 3s squared. Then we go a little further. I have to fill in for x. So this becomes 2 times x times 2e to the 2s. Get 1/2 times y, which is s squared t to the minus 1/2 times 2st. Right now I'm only filling in for x's and y's. Do it in the next one. But then we need to go further because I have to fill in s's where there are t's. So this stays the same. This becomes 1/2 s squared t, which is s cubed, 2s times s cubed, 1/2 s squared t, which is s cubed, and then s squared. I'm not simplifying anything because it makes it easier to keep track of. Let me actually fill in the first one just so we see it. That's our first result. So this is particularly messy, but really it's like some derivatives and substitutions. There's not any simplification going on. There's no icky organizing, etc. But I wanted to do this one to demonstrate that the d's and the partials can be a bit tricky, that the branches can be different lengths. That's okay. Nothing wrong with that. Let's do one more example. Again, to make a point. Let's say find dz dx, where say z, let's say z is x squared y, and y is, say, x squared plus x. So very simple problem, right? So the tree that we draw, z goes to x and y goes to x, very short tree. So then our symbols, we've got partial, a partial, and a d. The chain rule says that dz dx, which makes sense because z is only a function of x at the end of the tree, is partial z partial x. That's the top branch, top root, plus partial z partial y times dy dx. Now, before we go any further, I just want to make the point here. There's a very important point I wanted to make. Notice in this equation, there's both a dz dx and a partial z partial x. These are different things, right? dz dx is the thing we're looking for. This is the derivative of z, treating it as a function of only x. Partial z partial x is just the bit considering that z equals x squared y. When we do this, these are not the same, right? If you think that they're the same, you might cancel them and get something wrong. So in this case, we fill on the right-hand side, right? So the point I want to make, let me just actually say something here. These are not the same, like these two things right here, right? The notation is different for a reason. This is why we have two different symbols. So anyway, the right-hand side, we get partial z partial x, which is 2xy, partial z partial y, which is x squared, and dy dx, which is 2x plus 1. Fill it in. In other words, substitute in for y. And we're done. Right? So the important thing here really was just to emphasize the notation, is that we have partial notation and d notation for very specific reasons, and we don't want to confuse those. So that's the last thing in terms of applying the chain rule, but in terms of like actually just using it manipulation-wise. But I want to give an example of a problem where this can be used, like an actual application. Let me clear the screen off and do one of those. So 3, application. And one I'll do is related rates, which may bother you because related rates in Calc 1 are very often, or Calc 2, wherever they're done, are very often a bit of a headache. They're a headache because you get these weird formulas that things need to be substituted in for. They can be confusing. There's a lot of work to do before you even sort of take derivatives, implicit integration, implicit derivatives, etc. So with the chain rule, it can be a little simpler. So let me give you an example of how this works out. Right? So suppose we have the following. Suppose an object moves along the x-axis at 2 units per second. And let's say, we'll call that object A. And an object B moves along the y-axis at, say, 3 units per second. And the question is, at what rate is the distance between them changing? When A is at x equals 20 and B is at, say, y equals 30. Okay. So just so we're clear on this, you've got the x-axis and the y-axis, and A is moving along here, B is moving along here, A is moving to the right. It doesn't say to the right, but I meant when I said along the x-axis at 2 units per second, I meant this way. And B is moving up here at 3 units per second. We want to know how far the distance between them is changing. Right? Let's do this. Let's let, say, let me use a capital D, be the distance between. So D depends upon these two. So in other words, if, for example, if a is at x comma 0 because it's on the x-axis, and b is at 0 comma y. Oops, let me write that correctly the third time. Then the distance between them, this is an easy calculation because what we have here is something like this. Pythagorean Theorem. This is the square root of x squared plus y squared. Now, we also know the following tree diagram, right? We know that the distance between them is a function of x and y, that we just wrote it down. We know that x depends upon t and y depends upon t. Right? The x and y both depend upon time. We don't have formulas for those, right? Like I don't have a formula that says x equals something and y equals something. Right? But we do know this. Right, so let me actually just write that down because it'll be helpful. Right, so here note, we don't in fact need it. We don't know x equals or y equals. But by the chain rule, we do know that d dt is partial d partial x dx dt, that's the top part, plus partial d partial y dy dt. Those we can all fill in, right? So d dt, so partial d partial x, we're looking at this guy up here. Derivative with respect to x is 1/2 x squared plus y squared to the minus 1/2 times 2x. dx dt, that we know because the object A is moving along the x-axis at 2 units per second, so that's 2. Right? So again, the line's not done, but let me just point this out here. This is 2. This is because A moves at 2 units per second. And then we have partial d partial y, which is 1/2 x squared plus y squared, so minus 1/2 times 2y, times dy dt, which is 3. And that, of course, right here, this is because b moves at 3 units per second. So we can simplify this a bit. All right, we get some cancellations of 2's. We get an x over the square root of x squared plus y squared. Or 2x rather, because one of the 2's cancels but the other one doesn't. And then we get a 3y over the square root of x squared plus y squared. So this is 2x plus 3y over that square root. And then we're interested at the specific time when x is 20, y is 30. So that change in distance will be 2x plus 3y over the square root of 20 squared plus 30 squared. So this isn't the easiest problem in the world. Let me end on one more. I'll clear the screen and do one more, but I want you to sort of stop and take a look at it. It's not overly difficult, right? We have this tree diagram that gives the relationship between the thing that we want, or the distance and the time, because we want d dt. The chain rule gives us that relationship right here, and then we just fill in the details. So, like I said, this isn't the easiest problem. I probably should have, these 2 problems that I'm about to do, well, the other one is possibly a little bit easier than this. So maybe if this one's confusing, then wait for the next one, and then come back to this one and see if it makes more sense. Let me clear the screen off and do one more. So let's do this one more. So it'd be sort of sound like a classic Calc 1 problem. So suppose that sand falls into a conical pile. Suppose the radius increases at, say, 2 centimeters per second, and the height increases at 4 centimeters per second. The question is, how fast is the volume increasing when, say, the radius is 10 and the height is, say, 15? This one might make a bit more sense, right? So the goal is dV dt, right? How fast is the volume increasing? dV dt at r equals 10, h equals 15. Now, what do we know? We know that the volume depends upon the radius and the height. And those depend upon time, right? So the reason those depend upon time is what's given in the problem, is these facts right here. Right, the information given. Right? Now, we know that volume depends upon radius and height, in the sense that the volume of a cone is 1/3 pi r squared h. I said 1/3 or root 1/2. Right, so that's not a hard one to remember, that a cone is always 1/3 of a cylinder. So a cylinder is pi r squared h, so it's 1/3 of that. Right? So here goes the chain rule. The chain rule says dV dt is partial v partial r times dr dt plus partial v partial h dh dt. And again, in the previous problem I didn't fill in the partials or the d's, but here we have two partials and we have two regulars. So the chain rule gives us this last line on the page, and we fill those in. So partial v partial r is 2/3 pi rh. Partial r dt, radius is increasing at 2 centimeters per second. Partial v partial h is 1/3 pi r squared. dh dt, in this case, is 4. And so then we look at r equals 10, h equals 15. Let's plug that in. Plug those both in. 2/3 pi r h times 2 plus 1/3 pi r squared. Oops, fill in the r. Times 4. And that can be simplified at your leisure. So these are just kind of couple applications of the chain rule that are interesting. Now, the chain rule will also come up in some other places where it'll be used slightly more abstractly. I'm not going to worry about those because we don't have a context. So right now, the key thing to understand is how it works in terms of the tree diagram, how you get the final string of multiplication and addition, and how these simple related rates problems can work. And that is the end of that section.